Okay, here we are. Give it a few seconds to make sure the live stream is working and the audio is working. Let's see. Just a moment. Hello, hello, hello. Let's see. Okay, it's working fine. Very good. And I've got the chat out already. So let me go to. Here we are. So yeah. Next question is uncrossed lines. So we get that one going now. I think I have the right title. Let me just make sure I have the right title. Yeah, I do. Okay, very good. So, here we go. You are given two integer arrays, nums1 and nums2. Right? We write the integers of nums1 and nums2 in the order they are given on two separate horizontal lines. We may draw connecting lines, a straight line connecting two numbers, nums1 and nums2, nums1 of I and nums2 of j, such that nums1 of I is equal to nums2 of j, and the line we draw does not intersect any other connecting non-horizontal line. Excuse me. Note that a connecting line cannot intersect even at the endpoints, i.e. each number can only belong to one connecting line. Return the maximum number of connecting lines we can draw in this way. Okay. 1, 4, 2, 1, 2, 4, 2. We can draw two uncrossed lines as in the diagram. We cannot draw three uncrossed lines. So this seems like a computational geometry question. I don't know. Let's see. We cannot draw three uncrossed lines because the line from 1, 4, and nums2, 2 equals 4 will intersect the line from nums1, 2 equals 2 to nums1 equals 2. Okay. Alright, the lines have to be equal to each other. Cannot intersect any other connecting non-horizontal line. Connecting line cannot intersect even at the endpoints. Each number can only belong to one connecting line. Maximum number of connecting lines we can draw this way. Okay, I don't know the answer to this. This is kind of a unique question for me. Only 500 elements each. Okay. And the values are between 1 and 2000. Alright, pretty interesting question. I, again, don't know the answer. High acceptance rate, so maybe it's not that hard. So, okay, I mean, basically I think we just want to take the leftmost element each time. So for a given 1, we'd want to have 1 connected to 1, then 2 we would connect to 2, and then 4 we would connect to 4, but it crosses, so we wouldn't take that value. Yeah. Something like that. Basically, you want both elements to be minimal, so you get to pick when you see two elements. If they're equal to each other, then you would progress to the next step. These aren't equal to each other as well, nums1 and nums2. Yeah. Well, that's another thing too. You want to keep these indices as small as possible. So you see 1 and 1, you can skip those. You see 2 and 4. In both cases, the index is the same. So you probably want the smaller index. In the case that they have a tie, I think you want the index of the smaller array. Right? You want the smallest. So you'd want the index of the larger array. So if this had one more element, you go to 2, rather than going to 4. Because maybe you could have a 4 here, and then you can get to 4 here. That's for tiebreakers. You just take the smaller array. But in every case, you want to just minimize. Yeah, so a greedy algorithm, I think, is the way to go. I think you can do it in linear time. Okay, do I have a proof that that's correct? I don't have a proof. I would say it's probably true, because if you could find a solution that has more crossing lines, necessarily it would require, like, basically the smaller indices you have from left to right, the more options you have, right? So if you get the same number of crossing lines, but one of the indices is smaller on one side or the other, or really both indices are smaller, then that's a better solution. Necessarily a better solution. I think that's correct. Yeah. Yeah, also because your new line is not going to cross. Because your new line is not going to cross the previous lines, and we're going to try to assign every element left to right. Yeah, necessarily the next indices are going to be larger. All the possible indices that we get next are going to be larger. So we want to minimize all of those indices. It's always going to be the next one to the right. Either this one goes somewhere or this other one goes somewhere. Now, I could be wrong, like maybe it's better to skip. Maybe I should use dynamic programming. And I could pick this one, or neither, right? Maybe I should just DP this. I mean, if it's only 500, 25,000 DP is actually pretty reasonable. Maybe DP is the way to go. I'll just DP it. It's easier. That's fine. DP is fine. I think for each index, each integer, I can put the next index in a stack as well. Can I do it that way? Where the next element is. Trying to think if that's if that matters or not. I could put all of the elements in like what their indices are for all of the elements. And then binary search. But that seems like there's gotta be a better way to do it than that. That would give me n squared log n time, which will be fast enough for this question, but I think there might be a better way to do it. I mean, that's fine. We could just do it that way. That's good enough. That's good enough. I'm sure there's a better way to do this, but let's just go with that. It's gonna be val indices. I guess we gotta do 1 and 2, right? Something like that. Something along these lines. And I'm not sure now. I don't know if I actually need to do all that. Gee. Oh, no kidding. Yeah. That's so confusing. It's actually, I see. That's really confusing, actually. I'm not doing this correctly, the way that I'm... Never mind, forget all this. That's incorrect. I was thinking there's a way to do a DP, but that doesn't quite make sense. Oh no. I was thinking like I could just like do a double loop for each I and for each J. That actually... Oh boy. Excuse me. Oh no. Let me go lay down for a minute. I think I have the wrong answer here. I'm gonna go put my headset down and think about it for a minute. Yeah, I'm thinking about this like as a similar question to like the edit distance, but actually it's a little more complicated than that. I want to try to use a dynamic programming solution, but I don't think it's quite what I was thinking. I gotta like ponder a little bit more. I think DP is fine. I suspect you could actually do this using some kind of greedy algorithm, but yeah, I don't know it offhand. Let me think about it for a little bit longer. I'll come back to it. Let me think about it. spent, 20-30 minutes or so just sitting there thinking, laying down thinking. But I think I came up with a DP algorithm that's quadratic time. It's a little bit sophisticated, a little bit involved, but it's not too bad. So the basic idea goes like the following. Consider moving from right to left here, and the idea would be, let's say we're going back to front. We're going to start on the right side, right, of both arrays, and we're going to say, okay, in the first array there's some element. In the second array, what I want is I want to move right to left in the second array, and if the element in that second array matches this element, then what I'm going to do is I have some DP number that lets me know what the DP array of some sort that lets me know what the maximum number of lines that don't cross I can have if I were to look at the elements to the right. So in other words, I'm looking at two elements I and j. If I were looking at elements I plus 1 and j plus 1, what the maximum number of lines I can have is. Now, I can then take I plus 1 and j plus 1, where there's a line that can be drawn there, and say, okay, take I plus 1, j plus 1, that number, add 1 to it, write that in at I plus 1 and j plus 1. And then what I can say is, okay, whatever that value is, let that be like we'll say my maximum, my current best, we'll just call it best. The best is 0. Whatever that number is that I just got, set best to the maximum of best and that value. Now what I'm going to do is I move right to left. I'm going to write in at j minus 1, j minus 2, etc., all the way down from right to left. I'm going to write in one of two things. It's going to be either write in best, if best is better than whatever value is there currently, which would be I plus 1, and we'll call it k, where k is less than j. If best is better than whatever's at position k, write best in there. Also, if I see another number that matches, I can take a look at the DP value again at k plus 1 and I plus 1, and then say, add 1 to that value. If it's better than best, then update best again, and also try to update at this spot with best. So there's a best value that keeps getting updated, and there's also a DP value that keeps getting updated. And that goes right to left for each value I loop through each value j, performing that. And I can do this with using two integer DP arrays, DP1 and DP2, and use buffers. And these are going to be m is going to be nums1.size, and n is going to be nums2.size. And this is going to be of size n. Hopefully this makes sense. All initially 0. It may not always need to be 0, but I'm going to start off with 0. It's going to be the second array of values. Obviously, you could swap these vectors if you wanted to optimize memory as well, but it's not that necessary. So we're going to say for int I equals n minus 1, and for int j equals n minus 1. We're going to say const int val is nums of 1 of I, and we're going to say best always starts off at 0. So best is going to be maximum of best, and dp, let's say it's dp1, and we're going to write into dp2, and then we're going to swap. Copy dp2 into dp1, and then erase dp2. Right, reset dp2. So we're going to write into dp1 each time and return the maximum value of, it really should just be dp0, I think, of dp1 at the end of it. Okay, so the way this is going to work, it's going to be first things first, dp1j is the best, and then we're going to say dp1 of j itself is going to be equal to the maximum of itself and best. I don't know, we're going to write dp2, excuse me. Yeah, write into dp2 based off of dp1. And we're going to say also if nums of 2 of j is that's equal to value, then we can take best and set that equal to the maximum of itself, and dp1 of j plus 1 plus 1. So it's a little bit confusing, but that's an update to the value for best. And then we can update dp1 of j, also update best based off of dp1 of j, and then finally update dp2 of j based off of whatever best is. This is a little bit confusing, I realize. I think this should always just be set to best, actually. Yeah, in both cases, it's always going to be the best one, best value. Okay. Now, what's interesting about this is we just say and. We say j plus 1 is less than n, right? Otherwise, otherwise there's no dp1 of j plus 1 to look at. Yeah, we could actually increment both of these. That's fine too. In which case we could just say we don't need the if statement if we do it that way. Yeah, in which case it's actually going to be of these three. It could be just dp1 of j. It could be dp1 of j plus 1 plus this other value. Or it could just be itself, right? Whatever is the best of those three. That's what we're going to set dp2 of j to. And it starts off at 0 initially. I think that's it. Something like that. A little bit confusing, but something along these lines is what we want. Unknown network error, okay. Let me refresh the page. I might do it on time. Let's see if there's any comments here. Okay. Let me refresh. Cloudflare. I don't know what that is. I've seen that before, but I don't know what that is. I think there's something up with my network. Oh look, it's correct. G. that's it. I think that's it. Let me try some other stuff. 2, 3, 4, 5. 1, 2, 3, 4, 5, and then 5, 4, 3, 2, 1. 5, 4, 2, 1. Let's try some random things. 1, 2, 1, 2, 2, 1, 1, 1, 1, 2, 2, 1, 2, 1. And then some other stuff. 1, 1, 2, 2, 1, 1, 1, 1, 1, 2, 1, 2. Right, let's try some random things. Okay, I didn't really prove that this is correct, I just think it's correct. Let's do something else with this. 1, and 2, and then 1 and 1. And then, I don't know, just some random numbers. Just a bunch of random stuff. See if I can sort of catch the algorithm off at all. Okay, so I'm not sure if this is correct or not. I didn't, like I said, I didn't really prove it. I think it's right. I'm gonna go for it. It could be wrong. This could be something I didn't think of. Oh, looks like I got it. Sweet, not bad. Okay, that wasn't terrible. I mean, it took like an hour to figure that one out too. It took a while. I'm not sure what else I have to say about it other than it's like a space efficient DP algorithm. It's reasonable. Let's submit it like 5 times total. Yeah, I mean, it's relatively fast. It's not the fastest. There might be a faster solution that's linear time. You know, not sure what to say about this. It just took me a while to think it through. Yeah, I don't really have a lot to say. It's an interesting question for sure. 1, 2, 3, 4. We'll submit it one more time. I think what I'm going to do is submit it one more time, and then probably take a break for the day. Take a break. Okay, I got 7 milliseconds is like 90%. It's reasonable. I kind of wish I figured this out a little bit faster though. It's like it's okay. It's okay. It's not crazy good, but it's reasonable. So yeah, that's that one. Thank you for watching, and I don't know what else to say here. Have a good rest of your day. If you like the video, don't forget to like it and follow the stream. Subscribe. I'm gonna go ahead and stop here. I think I'm gonna take a break for the day. I don't think I'm gonna keep going. I think that's probably enough. So yeah, take care. Take care. Talk to you soon.